Welcome back to the channel. Today we're diving into one of the most visually exciting topics in physics, horizontal circular motion. From a car rounding a curve, to a ball being swung on a string, to a rider spinning on an amusement park ride. Objects moving in a circle all follow the same fundamental rules. But what keeps an object moving in a circle? How do we calculate the forces involved? In this video, we'll break down force, velocity, radius, and the physics that make circular motion happen. We'll look at diagrams, we'll walk through examples step by step, and make sense of how these ideas show up in real life. By the end, you'll see circular motion as a predictable and powerful concept that explains a lot of the world around you. Let's get started. Before we get started into this, we need to define some variables and talk about units. So I have an object going around in a circle, horizontal circle. We'll let R be the radius measured in meters. S will be the displacement or distance traveled. The V's will represent velocity or speed as it's going around. The period is the time it takes to go around the circle one time. We're going to let a capital T represent period. The units will be seconds per revolution. The frequency, we're going to let a small f represent that. That'll be the revolutions it makes per second. The frequency is inversely proportional to the period. We know that displacement or distance is equal to velocity times time. And the change in velocity is to the velocity as the change in displacement is to the radius. So if I take this is equal to S, if I place that here, replace that, then I can have the change in velocity is to velocity as velocity times the time divided by the radius. Let's isolate delta V. So if I cross multiply, delta V times the radius is equal to V times T. Divide both sides by R. The change in velocity is equal to the velocity squared T over R. From earlier lessons, you know that acceleration is equal to the change in velocity over time. So let's use that here. So I can say that acceleration is equal to velocity squared T over R over T. These two T's cancel. So I have a formula here then. It says that acceleration is equal to velocity squared over the radius. I'm going to put a small c here. So this will be called centripetal acceleration. So centripetal acceleration is equal to the velocity squared divided by the radius. Okay, this is a formula that we want to keep. It's a very important formula. We'll use it often. We're going to say that this velocity here is my angular velocity squared over the radius. All right, so we know this is going in a circle. So the circumference of a circle is 2 pi r. Okay, so let's see if we can put this into the above equation here. So this acceleration is equal to velocity squared over r. So this is going to be 2 pi r over t. Okay, that's the time it takes to go around once. Let's square that. And all this is over r. So then I can say then that the centripetal acceleration is equal to 4 pi squared r squared over t squared over r. This r and this square cancels. So I can say then that the centripetal acceleration is equal to 4 pi squared r over the period squared. A very important formula. We can write the same formula for frequency. So we know the relationship between frequency and period. So I can say then that the centripetal acceleration is equal to 4 pi squared r, and frequency is equal to the reciprocal of the period, so that would be frequency squared. Again, another very important formula. We also know that force is equal to mass times acceleration. Well, if I use centripetal acceleration, then I can say that the centripetal force is equal to mass times, if I use this above equation up here for acceleration, that'll be velocity squared over radius. Another very important formula. Now I can also substitute the 4 pi squared r over t squared. And I could also substitute mass times 4 pi squared r L squared. These are the primary formulas that we'll use. So make sure you set those aside somewhere. Another area of circular motion is like a car going around an unbanked curve, which means a car is on level surface. Centripetal force is pulling the car towards the center of the circle. That the force due to friction is going in the opposite direction. So I know then that the centripetal force is equal to the force due to friction. Okay, so we're going to say then that mv squared over r is equal to mu times the normal force. The normal force is equal to the weight, which is mass times gravity. We can say that the masses cancel. So v squared over r is equal to coefficient of friction times gravity. Okay, let's isolate the v squared. So v squared is equal to, I'll multiply both sides by r. So that'll be mu gr. So v will equal the square root of mu times g times r. So this is a formula that we'll use for our car going around an unbanked curve or a car turning on a flat surface. Okay, the next example is a car going around a banked curve, like a triangle. So on the yellow triangle here, I'm drawing a force triangle where weight is going straight down. The centripetal force is going to the center. Okay, so I have tan of theta. Tan is opposite over adjacent. So the opposite side is the centripetal force. The adjacent side is weight, which is mass times gravity. So tan of theta is equal to, we know that centripetal force is equal to mv squared over r over m times g. This mass and this mass cancel. Okay, if I simplify this a little bit, I would get tan theta is equal to v squared over rg. If I cross multiply, I can solve for velocity. So velocity squared is equal to tan theta times r times g. So the velocity is equal to the square root of tan theta times r times g. This is a formula we'll use often if I'm given the angle. However, if I'm not given the angle, but if I'm giving the coefficient of friction, remember that the tan theta is equal to the coefficient of sliding friction. So we could substitute then. So velocity is equal to the square root of coefficient of sliding friction times the radius times gravity. So those are the two formulas that we can use depending upon what information is given. So if we're given the angle, we'll use the top one. If we're giving the coefficient of friction, we'll use the bottom one. The next example is a non-horizontal circular motion. Think of it like a tetherball going around a pole. Okay, in the white, I have a distance triangle. On the bottom, yellow, I have a force triangle. Okay, so I can say again that the tan of theta is equal to the opposite, which is the centripetal force, over the adjacent, which is the weight, or mass times gravity. So we can say tan theta is equal to mass times velocity squared over radius over mass times gravity. The two masses cancel. We can simplify this to velocity squared over rg. Velocity squared is equal to tan theta times r times g. Velocity is equal to the square root of tan theta times r times g. So this is a formula we will use anytime I have a non-horizontal circular motion. For our first problem, The minute hand on a large clock is 0.5 meters long. Calculate the linear velocity at its tip in meters per second. All right, so visualize I have a large clock. The minute hand is the long hand. I'm just going to draw a shorthand here for the hour. Okay, so this is the minute hand. We're looking for the linear velocity. The linear velocity is equal to 2 pi r over t. So the velocity is equal to 2 times pi. The radius here is 0.5 meters long. All right, the period. How long does it take for this to make one revolution? Because remember, t is equal to seconds per revolution. So it takes 1 hour for that hand to go all the way around. 1 hour, that's 60 minutes. So that's 3,600 seconds. So velocity is going to be 2 pi times 0.5 over 3,600. This will be our meters per second. If I calculate this, I will get 8.73 times 10 to the negative 4th meters per second. The calculator will probably say 0.000873. Okay. So that's the answer to the first problem. In the second problem, we have a 30 centimeter disc rotating at 33.5 times per minute. What is the period? Okay, we know that the period is equal to the number of seconds per revolution. The time will go on the top, so I have 1 minute on top. And revolutions will be 33.5 revolutions. I need the 1 minute to disappear, so I know that 60 seconds is 1 minute. Minutes cancel. That would give me time in seconds over revolution. So if I were to multiply, I have 60 seconds divided by 33.5 revolutions. That would give me 1.79 seconds for each revolution. In a sample problem, I have a teenager twirling a 0.3 kilogram stone attached to a string 2 meters long in a horizontal circle. .3 kilograms. And that circle is 2 meters long. So that's the radius. Okay, so I need to find the velocity. Okay, so I'm going to say that the centripetal acceleration is going to equal to the velocity squared divided by the radius. Okay, I'm going to use 9.81 meters per second squared. It's equal to the velocity squared divided by 2. So the velocity squared is going to equal 2 times 9.81. So velocity is equal to the square root of 2 times 9.81. Plugging this into my calculator, I get 4.43 meters per second. That will be the velocity that it's traveling. All right, for the B part. How long does it take for the stone to travel once around? So how long does it take? That means I'm solving for the period. So I'm going to say that the centripetal acceleration, which is going to be 9.81, is equal to 4 pi square r over the period square. Okay, I'm going to rearrange this. So I'm looking for t squared. I'm going to switch these two places here. So t squared is equal to 4 pi r, 4 pi square r over a sub c. There we go. So t is going to equal the square root of 4 pi square r over a sub c. So the period is going to be equal to 4 pi square times 2 divided by 9.81. Okay, so that gives me that t is equal to the square root of 78.96 divided by 9.81. So that means that it's the square root of 8.049. So the period is equal to 2.84 seconds per revolution. And that will be our answer. Okay, in the next problem here, we have a 2,000 kilogram car. It's on an unbanked curve. It has a radius of curvature of 30 meters. You're given the coefficient is 0.75. So what's the maximum velocity she can travel through the curve without sliding? All right, since we're giving the coefficient of friction, we'll use that variation. So velocity is equal to the square root of coefficient of friction times radius times gravity. So velocity is going to equal 0.75 times the radius, which is 30, times gravity, which is 9.81. Plugging this into your calculator, you'll get 14.86 meters per second. So this will be the maximum velocity that she can travel around this curve before tires start sliding. In this problem, I have a 12 kilogram object moving in a circular path with a radius of 3.8 meters and a frequency of 0.24 revolutions per second. And we're looking for what is the centripetal force. So I know that the centripetal force is equal to the mass times the centripetal acceleration. Since we're given a frequency, I know that centripetal force is equal to the mass times 4 pi square r frequency squared. So the mass is 12 kilograms times 4 times pi squared times the radius, which is 3.8, times the frequency of 0.24 squared. Plugging this in the calculator, I get a force of 103.7 newtons. Princess is on an amusement park ride. Her mass is 52.4 kilograms, and the radius of the circle created by the ride is 8.2 meters. If the ride spins at 0.4 revolutions per second, calculate her centripetal acceleration. Okay, so centripetal acceleration is going to be equal to 4 pi squared r f squared, because we're given frequency. So centripetal acceleration is equal to 4 pi squared times the radius of 8.2 meters, and the frequency is going to be 0.4 squared. So the centripetal acceleration be 51.8 meters per second squared. A device for accelerating subatomic particles to high speeds is called a cyclotron. If a cyclotron has a radius of 80 centimeters, with what speed can protons be accelerated by magnets that supply a centripetal force of 1.2 times 10 to the negative 12 newtons? And you're given that the mass of the proton is 1.67 times 10 to the negative 27 kilograms. Okay, so we're looking for speed. Okay, so we got to keep that in mind. All right, we're given centripetal force. So we have the formula: centrifugal force is equal to mass times velocity squared divided by the radius. Let's cross multiply so that centripetal force times radius is equal to mv squared. Let's isolate the v here. So let's divide both sides by m. So I can say that velocity squared is equal to the centripetal force times the radius divided by the mass. So velocity is equal to the square root of the centripetal force times the radius divided by the mass. So the velocity is going to equal, all right, it says that the centripetal force is 1.25 times 10 to the negative 12 times the radius, which is 80 centimeters, which is 0.8 meters. And all this is divided by the mass. So the mass is 1.67 times 10 to the negative 27. So the velocity is equal to, let's say, 5.988 times 10 to the 14th power. So I can say then that the velocity is equal to, okay, my calculator says 2447.0439 meters per second. And we can write that a little neater to say 2.45 times 10 to the 7th power meters per second. So that will be the velocity needed for the proton. All right, great job working through horizontal circular motion. Now you will understand how centripetal force, velocity, and radius all come together to keep an object moving in a circle. If this video helped you, don't forget to like, subscribe, and share it with a friend who's studying physics. And as always, feel free to drop questions in the comments. Thanks for watching, and I'll see you in the next lesson. Goodbye.